Today's daily Leetcode problem of the day is minimum difference in sums after removal of elements number 2163. For this problem, we're given a zero-indexed integer array called nums consisting of 3 times n elements. We're allowed to remove any subsequence of elements of exactly size n from our nums array. The remaining 2 times n elements will be divided into 2 equal parts. So the first n elements belong to our first part, and their sum is equal to sum first. The next n elements belong to the second part, and their sum is sum second. So the difference in sums of the two parts is denoted as sum first minus sum second. For example, if sum first is 3 and sum second is 2, their difference is 1. And similarly, if you swap the values, their difference is -1. Our goal is to return the minimum difference possible between the sums of the two parts after the removal of n elements. So the core idea for this problem is we're going to use heaps to track the minimum and the maximum efficiently. So we're going to track the minimum value we can achieve on the left side and the maximum value we can achieve on the right side. We want n smallest numbers from the first half and the n largest numbers from the second half. And to do that, we're going to use a max heap to track the smallest numbers from the left to the middle, and a minimum heap to track the largest numbers from the right to the middle. So let's go ahead and jump into this code. First thing we're going to do is initiate a variable n, so int n, and n is simply the nums.length divided by 3. 3 divided by 3 is 1, our n here is 1. 6 divided by 3 is 2, our n here is 2. So that's all we're doing right here. Next thing we're going to do is build our first array, and this first array is going to store the sum of the n smallest elements. So from 0 until n times 2, because we're going to go halfway through the array. That's going to store the smallest elements. So we're going to initiate a long variable because we are going to return a long, so that means the numbers are going to get pretty big. So we're going to have a long, and we'll call this our part 1 because this is part 1 of the solution, and that's a new long of n plus 1. Next thing we're going to do is we're going to keep track of the sum. So our long sum is going to be initiated to 0, and then we're going to have a priority queue, and this is going to be our max heap. So it's going to store integers, and to initiate a max heap, we'll first identify it's our Q1, and it's a new priority queue. But for a max heap, we're going to need to initiate some sort of lambda function. So this lambda function is basically going to say we're going to take values a and b, and we're going to sort them by analyzing the difference between b minus a. So max heap, we're going to keep the largest values on top so we can pop out the largest values. So that's all this is saying, larger values on top. That is our max heap initialized. Next thing we're going to do is we're going to initialize our heap and our array with the first set of n elements. So we're going to use a little sliding window technique. So we're going to use a sliding window technique where we're first going to initialize it with the first n amount of numbers, and then we'll slide through and identify if there are smaller numbers we should keep and therefore get rid of our large numbers. So let's first initialize it by saying for each integer I is equal to 0, as long as I is less than the first n amount of numbers, I can increment, and our sum will plus equal nums of I. So each value will be added to our sum, and then we can add it to our priority queue as well. So we're going to add nums of I. So right now our queue is filled with the first n, and our sum has the sum of the first n numbers. And then we're going to initiate this is kind of our dynamic programming function. So we're going to initiate its first value to that sum. So part 1 of 0 is going to be equal to sum. This is the first calculated sum that we did by initiating all of the first n values. So that is the first n values sum. Next, we are going to slide our window from n to 2n minus 1. The reason we do 2n minus 1 is because 2n would be the middle minus 1 because it's 0 indexed. So let's go ahead and do that. For each integer I is equal to n, because that is where we left off right here. Then we can say I is less than 2 times n. And automatically, because we're using less than, not less than, equal to, it's 2n minus 1 where we will stop. Then I will increment through these values. And we'll do the same exact thing. We'll first add our current element, so sum will plus equal the nums of I value that we're currently looking at. We'll add it to our q, so q.1 will add nums of I. Then we're going to remove whatever the largest value is in this sub-array, or this half of our array. So we'll say, cool, now we have n plus 1 values. Let's go ahead and remove 1 to get it back down to n. So sum will minus equal q1.pull. And we can do this because we set up our priority queue to put the biggest numbers at top. So we will pull out the biggest number, and then our part 1 of I minus n minus 1, because now we're moving through our sliding window technique here, will be equal to the sum. So we're going to record the current smallest n sum, and that will be stored at I minus n minus 1. Cool. So that is our sliding window technique, and we will traverse the first half of our array, filling up with the smallest number and amount of numbers. Next thing we have to do is traverse from the end and compute our part 2 value. So that's part 1. Part 2 is going to be the maximum numbers on the right side of our array. So we're again going to initiate a long called part 2, and that's going to be equal to 0. And then this one will be a priority queue as well. However, for this one, we do not need to have a lambda function because it will automatically sort for the minimum values at top. So new priority queue. So this is our minimum heap. It's going to track our largest values. Now we need to initialize it with the last n elements. Same thing we did for part 1. So for each integer I is equal to, and then for this we're going to have to compute basically, we're going to compute the end of the array, and we're going to traverse backwards from the end of the array to the middle of the array. So 3 times n, as there's a total of 3n amount of elements, and then we're going to do minus 1 because it's 0 indexed. We're going to go backwards from here, so the middle point would be I is greater than or equal to 2 times n. And we can do greater than or equal to because we are including the middle of the array here. And then I minus minus. So this is going to allow us to go from the right side to the middle, initializing. And we'll do the same thing. So part 2 will plus equal nums of I. And then we will q2 dot add our nums of I. Just initializing this priority queue. Then we're going to walk backwards from 2n minus 1 to n. Basically, we are going to traverse all of those middle values again and update our part 2 sum and compute the minimum difference. So we're going to try to get all the largest values that might have been left out of our left array. Now they're going to be included on our right array. So long answer will be equal to part 1 of n minus part 2. The reason we're going to use part 1 of n is because that's our base case. So we're saying that we included all of the first n values in the front. That's our base case. We'll traverse through all of our created solutions up here in this next for loop. So in this for loop, we are going to update our part 2 value as we traverse, as well as update our part 1 value to find our smallest possible difference. So integer I is equal to 2 times n, because that's where we left off, minus 1, because we did include it above. Then, as long as I is greater than or equal to n, meaning we're including n, I will decrease again. So, same exact thing as before. We're going to say part 2 will plus equal our nums of I. Our q2 will dot add nums of I. And then we will subtract whatever the smallest or the top of the minimum heap is. So part 2 will minus equal our q2 dot pull, getting rid of the smallest value and returning our subarray back to n length. Then we can update our answer. So our answer will be equal to math.minimum answer of part 1 of I minus n. So we will be able to traverse all of our solutions we calculated for part 1 and the smallest value we have of part 2 up to this point. Then we can return our answer. It's as simple as that, if you could call that simple. So that passes our test cases, and if we submit it here, passes all solutions. So thank you, and follow for more daily Leetcode solutions.